Hello and welcome to another Stephen Mendes video. In the last video, we showed you how to find the initial and final conditions. So now we have a real circuit that you could find on your examination paper. And we are asked to find I for t is greater than 0 if the circuit is in steady state at t equals 0. What are the initial conditions and the final conditions? That's easy enough to find in this circuit because the inductor is a short at both initial and final steady state. It's just a piece of wire and it's shorting out the capacitor. So V is equal to 0 for both states. Remember, this is DC we're talking about. And once the field around the coil has collapsed or has become static, then the coil itself offers no resistance. The ideal coil offers no resistance to electric. So the coil in DC conditions, steady state, is actually shorting out the capacitor, and we replace it with just a piece of wire to draw two circuits, one for each of the sources with its attendant resistor. So the initial circuit is the 2 ohm resistor with the 10 volts, and the final circuit is the 3 ohm resistor with the 6 volts. So what happens when we switch our switch is actually that the current I drops from 5 amps at the beginning at t equals 0 plus to 2 amps after a long period of time. Make sure you understand that, but if not, watch the previous video. Let's keep going. Remember, we are solving for I. So we want to write equations for I that are going to show that I goes from 5 amps to 2 amps, and T is going to appear in the solution to show how it does that as each fraction of a second passes. So we start by writing a nodal equation at V. We use KCL at that node and we have 3 terms. We have the initial 6 volts minus V over 3. Notice that this is at t 0 plus. We are concerned with the new voltage and resistance after the switch has been thrown. And it is negative because the current is flowing into the node, whereas 2 and 3 are flowing out of the node. So I is flowing out in 2, and for 3 we have the capacitor formula, 1 over 12 is C, dV equals 0. So hopefully that equation is not going to stumble anybody. So the next thing is to find another equation to connect I with V, because we have 2 unknowns, I and V, in that one equation. So the next perfect equation is the inductor equation itself, which gives to us 4 di dt equals to V. So that connects I and V, so we have to put that now into the other equation. So we substitute to remove V from our first equation by inserting our 4 di over dt. Now in the last part, we have dv dt. We're replacing dv dt, and you will notice that we have gone to the second derivative, d2i over dt squared. Now let us observe what happens there. We have to differentiate V. So dv dt means that we have to differentiate di dt. And when we differentiate di dt, it becomes the second derivative, or d2i over dt squared. If you don't understand that, then you don't know calculus, and that's why we have this red thing. Go to Calculus for Dummies. It's a good book. I have used them. All of these books for dummies are excellent and well explained. You don't have to strain your brain or feel bad. We all are born not knowing, and we got to get the knowledge some way. And the best way is to buy the book for dummies. But it's the easiest way. You can buy other books, but it will take a lot longer to master than if you buy the dummy book. So plug for all the dummy series, and thanks to those who make them available to help people like you and me. Now, we are going to continue with our story, so we put back our equation once you agree that that is actually our equation. And we need to expand it. We need to remove the brackets and collect up terms. So I've missed a few steps there, but make sure that you agree with me that after we remove the brackets and collect up terms, which is simple algebra, we end up with that. And we want to get rid of the 4 over 12 because ideally we would like to have our second derivative with a power of 1. It makes for easy use of the formula. So the next step is to divide throughout by 4 over 12, and that gives us nice numbers in the final simplified expression. So I'm sure you can handle the algebra. If not, you might want to look for a book called Algebra for Dummies. But for right now, it's just simple algebra to expand and reduce our equation to a simple equation, which is referred to as a second order linear differential equation. That's what that equation that we're staring at is called. Okay, now I'm making it easy for you. The second order linear differential equation has a natural response, which is achieved by replacing the 6 with a 0. The 6 on the right is replaced with a 0, and then we can use a quadratic expression. Remember, x squared plus something x plus something. What happens? We end up with a quadratic equation in A, B, and C. And we use our quadratic formula, minus b plus or minus the square root of b squared minus 4ac all over 2a. But our a is 1. We've made sure to get rid of the constant in front of our x squared term. So that's a quick shortcut method to use anytime you see a second order linear differential equation. The natural response of the equation is with the right member as 0. 6 comes about in our right hand member because of the fact that it is being driven by some voltage. But let us not get ahead of ourselves. We have 2 roots. Now, when we use our quadratic equation, you can only end up with 2 real roots as shown, a pair of identical roots, or a complex root if what comes under that square root sign is a negative number. In our case, the result is 2 real and different roots. So therefore, when that happens, the circuit is overdamped, and we pick, P-I-C-K, from a number of solutions. Our overdamped condition requires that we use the solution in purple. If we had 2 equal but real roots, we would choose our solution in green. And finally, if we ended up with a negative number under the square root, we would choose our solution in orange. So we proceed with the overdamped solution. But notice, look at them. The solution is for the natural response. It's going to end up at 0 because eventually those exponential terms, as t gets larger, are going to all end up as 0. And our final result of I is not 0 at all. We calculated what our final result was at the beginning when we calculated our initial and final conditions. Our solution has to end up with I equal to 2 amps at the end. So the best way to do that is simply to add the 2. That way, when the first 2 natural response members become 0, our I will be 2 at the final state, which is what we so desperately want. Now we can proceed to find the A1 and A2. These A1 and A2 that appear in all our differential equation solutions are constants that only depend on the initial conditions. So let us see how we find them. Our initial current was 5 amps at t equals 0. At t equals 0, the exponential terms all become 1 because any quantity raised to a power of 0 is 1. So make sure you understand that at t equals 0, those exponentials disappear and we have 1. So when we multiply A1 by 1 and A2 by 1, we just have A1 plus A2 plus 2 must equal 5 amps. So that's one equation that will help us to discover what A1 and A2 actually are. We need another equation, so we want to differentiate our solution to get that. Now, when we differentiate our entire expression, we take the powers and we bring them down and just multiply the e's by the powers. So we have minus 1t. So minus 1 makes a minus sign in front of the A1. We have minus 3t. So we bring down and we put the minus 3 in front of the A2. And the 2 disappears because it's a constant. Constants disappear under the action of the differential operator. So from our original equation, we had 4di equals to v. That was one of our original equations, the equation for the coil. But we saw that the capacitor had no voltage at t equals 0. So if we substitute 0 for v, then di dt itself becomes 0. And if di dt becomes 0, we can plug 0 into the left of our derivative at the top. And that will give us another equation to use to find the A1 and the A2. So now what we do is we have our two equations that are going to allow us to find the A1 and the A2. And we rearrange the first one to make A1 the subject. So by doing that, we have an equation which only gives us A2. Because we substitute for the A1 in the second equation, and then we are able to find A2. Now, once we have found A2, we can plug it into the equation which will give us the A1. Two equations, two unknowns. Make sure you realize that you solve. This is all linear stuff. You did this in little children. So this is great. But now we have our A1 and A2, and we can write our final answer. I equal to 4.5 e to the minus t minus 1.5 e to the minus 3t plus 2. That is the total solution from t equals 0 to a big T when the 2 disappear and we're just left with I equal to 2. So I moves from 5 down to 2 over time using this wonderful equation. This has been a long video. Thanks so much. Keep watching the Stephen Mendes channel and we'll see you in the next video.